On July 3, 1845, a crowd of naval officers gathered at the Devonport Dockyard in England to watch a test that would end a building method older than the Roman Empire. On one side of the yard, a crew of 30 men hauled on ropes tied to a 2,000-pound iron block, hoisting it up a wooden frame and letting it drop onto an oak pile driven into the riverbed. They had been doing this since dawn. 12 hours of hauling, dropping, and hauling again, and the pile had barely reached its target depth. On the other side of the yard, Scottish engineer Nasmyth stood beside a machine that none of them had ever seen in operation. A 4-ton hammer block powered by steam, mounted on a wheeled iron frame that traveled on rails. The Lords of the Admiralty had arrived that morning by coincidence, expecting a routine dockyard inspection. What they witnessed instead changed construction forever. Nasmyth's machine drove a 70-foot pile, 18 inches square, to full depth in 4.5 minutes. The same pile that had taken the manual crew 12 hours. That is a speed increase of roughly 160 times. In the time it took the old crew to eat their lunch, Nasmyth's steam hammer could have driven a dozen piles. But what Nasmyth's invention actually replaced was far stranger, far older, and far more deadly than anyone watching that demonstration fully understood. For over 2,000 years, every bridge, every wharf, every building on soft ground was held up by wooden stakes hammered into the earth by human muscle. And the men who did that work paid for it with their hearing, their limbs, and often their lives. This is the story of pile driving before hydraulics. It spans 25 centuries, from the Roman legions on the Rhine to the steam-powered rigs of the American Railroad, and it is one of the most overlooked chapters in construction history. We are going to cover this story in 4 parts. First, the ancient and medieval methods that survived for 2,000 years. Then the moment steam power broke through in 1845. Then the American expansion, including Civil War innovations, and the mega projects that pushed deep foundation work to its limit. And finally, the human cost and the transition to the modern era. To understand what Nasmyth's machine replaced, we need to go back much further than the 1800s. The earliest written description of a pile driver comes from the Roman architect Vitruvius, who wrote about foundation methods in his treatise De Architectura around 25 BC. Vitruvius recommended driving wooden piles into marshy ground to support heavy structures, but he refused to describe the machine itself. His exact words translate roughly to, "There are innumerable mechanical devices about which it does not seem useful to enlarge, because they are to hand in our daily use." In other words, pile driving was so common in the Roman world that he did not even bother explaining how the device worked. The Romans called their pile driving device the fistuca. It was essentially a heavy iron weight lifted by ropes and dropped repeatedly onto the top of a sharpened wooden stake. Julius Caesar described using this method in 55 BC, when his legions built a timber bridge across the Rhine River in just 10 days. The soldiers drove oak piles into the riverbed using the fistuca, while Germanic tribes watched from the far bank. Caesar needed the bridge to demonstrate that Rome could reach anywhere. It served its purpose, and he had it torn down after 18 days. But the method his soldiers used to build it would remain virtually unchanged for the next 19 centuries. Think about that for a moment. The fistuca that Caesar's soldiers used in 55 BC worked on the same principle as the pile-driving rigs operating on the London docks in 1840. The weight got heavier, the frames got taller, but the fundamental idea of lifting something heavy and dropping it on a stick did not change for almost 2 millennia. By the medieval period, pile driving across Europe had settled into 3 basic machine types that historian Marjorie Nice Boyer documented in her landmark 1985 study published in the journal Technology and Culture. Boyer spent years in European archives studying construction accounts, patents, and engineering drawings. What she found was extraordinary. The first machine was the simple hand ram, where 2 or 3 men stood on a wooden platform and lifted a log between them, dropping it onto the pile head. Paintings from 15th century Florence show exactly this method in use along the banks of the Arno River. Boyer's observation was blunt. The technique could equally well have been employed by the prehistoric lake dwellers of Switzerland. The second machine was the engine, also called the gibbet ram or running ram. This was a tall wooden frame with a heavy iron block suspended on a rope that ran through a pulley at the top. Instead of 2 men lifting the weight, a team of 14 to 30 workers hauled on individual cords tied into one great rope, pulling the block to the top of the frame and then releasing it to fall onto the pile head. Accounts from the Orleans Bridge construction between 1387 and 1389, preserved in the Archives du Loiret, record gangs of 14 to 16 men pulling on the ram throughout the day. Pile driving season at Orleans was deliberately timed to coincide with low water. When out of work, boatmen could be hired cheaply for the back-breaking work of hauling on those ropes. The output was pitiful by modern standards. A gang using the engine could deliver perhaps 30 to 40 blows per hour. Each blow required the entire team to haul the ram back to the top of the frame. After 20 to 22 consecutive blows, the crew needed a rest pause before they could continue. Driving a single pile to its full depth could take an entire day. If you are finding this valuable, hit like and subscribe. We cover the forgotten history of construction every week. The third machine was the haie, a pile driver that used a windlass to lift the weight instead of a team of men pulling ropes. On paper, the windlass should have been a clear improvement. Fewer men, less effort per blow, more consistent delivery. But builders across Europe rejected it for centuries. In 1595, an Amsterdam carpenter named Lamprecht Gerrits received a 10-year patent from the States General of the Low Countries for an improved windlass pile driver. He claimed his machine could operate with 6 or 7 men instead of the standard 28 to 30 required for the engine. The patent was granted and recorded in the Dutch archives. The machine did not catch on. Boyer spent years trying to understand why European builders resisted a clearly superior technology. Her conclusion was one of the most striking observations in the history of construction. Before the Industrial Age, she wrote, labor was cheap and materials were expensive. People probably preferred full employment to efficiency. There was no economic reason to build a better pile driver when you could simply hire more men. The timber for the piles cost more than the labor to drive them. Engineers from Lorini to Leonardo da Vinci drew elaborate pile driving machines in their notebooks. Job sites kept using the 14th century equipment because the economics favored it. That is a 2,000-year span of almost zero technological progress in one of the most fundamental operations in all of construction. The empires changed, the bridges got longer, the buildings got taller, but the man hauling on the rope in 1840 was doing essentially the same job, using essentially the same machine, as the man hauling on the rope in the year 140 AD. And then, James Nasmyth changed everything in 4.5 minutes. Nasmyth did not set out to build a pile driver. He had invented the steam hammer in 1839, originally designed for forging large iron components at his Bridgewater foundry in Patricroft near Manchester. The steam hammer was itself a dramatic machine. A heavy block of iron lifted by a steam piston and dropped with precisely controlled force onto a workpiece below. Nasmyth's genius was the precision of that control. The same hammer that could flatten a red-hot iron bar could also crack an egg placed in a wine glass without breaking the glass. He demonstrated this trick repeatedly for visitors to his foundry, and it became one of the most famous party tricks in Victorian engineering. By 1843, Nasmyth recognized that the same principle could drive piles far faster and more consistently than any human crew. He listed the invention of the steam hammer pile driver as item 25 on his chronological inventions list. The Devonport Dockyard was expanding its key ham yard facilities, and the project required an enormous amount of piling work. Nasmyth wrote in his autobiography that an immense portion of the shore of the Hamoaze had to be walled in so as to exclude the tide, extending 1.25 miles in length, requiring a vast amount of pile driving. The machine he built for Devonport was elegant in its simplicity. A 4-ton hammer block, a steam cylinder, and a guide box all rested as dead weight on top of the pile while it was being driven. This was the critical detail. The entire mass of the machine added to the driving force with every blow. The same boiler that fed the steam hammer also powered a small locomotion engine that moved the rig on rails from one pile position to the next, and a rearing engine that hoisted the next pile into the leads and held it vertical. The result was 80 blows per minute, each one delivering the full weight of the falling hammer block plus the dead weight of the entire assembly pressing down on the pile. Compare that to the manual crew across the yard. 30 men, 30 to 40 blows per hour. Rest pauses every 20 blows. Nasmyth's machine delivered 80 blows per minute. The math was devastating. Steam was not just faster than muscle, it made muscle irrelevant. The Key Ham Yard project was followed by the high-level bridge at Newcastle upon Tyne, where Nasmyth's machines drove the foundation piles for Robert Stephenson's combined road and rail bridge high above the River Tyne. From there, the technology spread to Egypt, where steam pile drivers were used on the Nile barrage, and to dockyard projects across the British Empire from Bombay to Singapore. But the spread was slower than you might expect. Nasmyth's machine required a steam boiler, a supply of coal, skilled operators, and a rail system to move between pile positions. On a large dockyard project with hundreds of piles to drive, the investment made sense. On a small bridge job in a remote location, it often did not. The economics of steam pile driving favored concentrated, high-volume projects. For the thousands of smaller construction jobs across the countryside, manual pile driving continued well into the 1880s and beyond. There was also the matter of risk. A steam boiler on a construction site was a potential bomb. Boiler explosions were a leading cause of industrial death throughout the Victorian era, and a pile driving rig sitting on wet, unstable ground near a riverbank was not the safest environment for a pressurized vessel. The trade press of the period carried regular accounts of boiler failures on construction equipment. Workers accepted the risk because the pay was better than hauling ropes, but the danger was real. The age of human-powered pile driving was ending. But it would take decades for the steam hammer to reach every job site, every harbor, every remote railroad crossing. And in the meantime, the old methods continued to maim and kill. Across the Atlantic, the American adaptation of steam pile driving took a different path. The key patent was not Nasmyth's. It was United States Patent 160,781, filed by Thomas T. Loomis in 1875. Loomis adapted Nasmyth's self-acting principle for American conditions, and his design became the foundation for the company that would dominate American pile driving for the next century. That company was Vulcan Iron Works, founded in 1852 by Henry Warrington, a Manchester-born engineer who had emigrated to Chicago. Originally a general foundry producing castings and machine parts, Vulcan began manufacturing pile hammers under the Loomis patent starting in 1875. The early machines were crude compared to what came later, but they worked. An improved design called the Skinner hammer was in service on the Chicago and Alton Railroad pile driver car by April of 1882, and a testimonial from General Roadmaster W. Riley, dated October 30th of that year, confirmed its reliability on railroad bridge construction. The first Warrington Vulcan No. 2 hammer general arrangement drawing is dated February 9, 1887, serial number 6, shipped to the Marquette, Houghton, and Ontonagon Railroad in Michigan's Upper Peninsula. By the turn of the century, Vulcan offered 3 standard sizes. The No. 4 carried a 550-pound striker for driving sheet piles. The No. 2 used a 3,000 pound striker for medium foundation work. And the No. 1, the heavy hitter, dropped a 4,800-pound striker for major bridge and wharf construction, all 3 models running at 60 to 70 blows per minute. These machines were the workhorses that built the railroad bridges, harbor walls, and building foundations of industrial America. But perhaps the most fascinating chapter in American pile driving history comes from the Civil War. Brigadier General Herman Haupt ran the United States Military Railroad, and his operations at Aquia Landing, Virginia, and the Alexandria Railroad Wharf included steam pile driver cars mounted on flatbed rail wagons. These machines were photographed by A.J. Russell, and the images survive today in the National Archives. Haupt organized his pile driving crews into 10-man squads by June of 1862 and used them to rebuild destroyed railroad bridges at extraordinary speed. Haupt was an engineer before the war, a graduate of West Point, and a veteran of railroad construction. He patented his own improvements to pile driving valve gear under United States Patent 43,910, filed August 23, 1864, covering improvements in balance valves applicable to steam hammers, drills, pile drivers, and mining machinery. But Haupt's real contribution was proving that pile driving could be organized as a military operation, with standardized equipment, trained squads, and ruthless efficiency. The Potomac Creek Bridge stood 400 feet long and nearly 100 feet high over a deep ravine in northern Virginia. Confederate forces had destroyed the original bridge. Haupt's crews rebuilt it in 9 working days in May of 1862, using 2 million board feet of locally harvested timber. The pile driving went on around the clock. Abraham Lincoln visited the site on May 28th and told his colleagues that Man Haupt has built a bridge upon which loaded trains are passing every hour. And upon my word, gentlemen, there is nothing in it but corn stalks and bean poles. It was the highest compliment Lincoln could give. The bridge looked impossible, but it carried trains, and the piles that held it up had been driven by steam. If you are finding this valuable, hit like and subscribe. We cover construction history that no one else does. Now we move to the projects that tested these machines to their absolute limits. We should start by correcting a myth repeated in nearly every documentary about the Brooklyn Bridge. The Brooklyn Bridge used no driven bearing piles under its towers. None. The Brooklyn caisson, a massive timber and iron box 168 feet long and 102 feet wide, weighing 3,000 tons, was sunk through river silt to bedrock at 44.5 feet below the water. The Manhattan caisson, slightly larger at 172 feet long, went down to 78.5 feet, where Chief Engineer Washington Roebling halted the excavation. He concluded that the additional 30 feet to bedrock could not be safely reached using compressed air. Each caisson was then filled with concrete and brick, becoming a solid monolithic foundation. The caissons are the foundation. Every source that shows driven piles underneath the Brooklyn Bridge towers is confusing 2 different things. The timber guide piles that kept each caisson descending vertically into the riverbed are not load-bearing foundation piles. They served a positioning function during construction and carried no permanent load. That distinction matters because it reveals what the Brooklyn Bridge actually was. It was not a conventional pile-supported structure. It was a direct-to-bedrock gravity foundation on the Brooklyn side and a friction and weight foundation on the Manhattan side. The engineering was far more daring than the simplified version suggests. The single most haunting pile-related fact at the Brooklyn Bridge has nothing to do with the towers. It happened before a single stone was laid. On June 28, 1869, Chief Engineer John Augustus Roebling was standing on a cluster of wooden pilings at the Fulton Ferry Slip, surveying the site for the Brooklyn Tower, when an arriving ferry crushed his foot against the timber. He refused amputation. Tetanus set in within days. He died on July 22, 1869, 3 weeks after the injury, and his son Washington took over the project that would become the most famous bridge in the world. The Brooklyn Bridge began with a death on a pile. Project physician Dr. Andrew Smith documented the toll of caisson disease during the Manhattan Foundation work. Between January through May of 1872 alone, Smith treated 110 cases of decompression sickness among the workers inside the pressurized caisson chambers. 3 workers died directly from the condition. The total project death toll is usually estimated at around 20, though the true number remains uncertain because many laborers were immigrants whose injuries were never formally recorded. The Eads Bridge over the Mississippi River at St. Louis, built between 1867 and 1874, is the project that actually pushed deep foundation technology to its absolute limit. The East Pier caisson reached bedrock at 95 feet below the river surface, 119 feet below the city directrix reference elevation. The West Pier reached 86 feet below the surface, 51 feet below the river bottom. These were the deepest pneumatic caisson foundations attempted anywhere in the world to that date. In August of 1867, a flotilla of pile drivers, workboats, derricks, steam engines, and barges gathered at the foot of Washington Avenue on the St. Louis waterfront. That fleet gives you a sense of the scale of deep foundation work in the 1860s. Dozens of vessels, hundreds of workers, all focused on getting 2 stone piers anchored to the bedrock of the Mississippi. The caissons at EADS Bridge were held in position during sinking using timber guide piles driven into the riverbed, plus 10 lateral suspension screws, each 20 feet long, mounted on each side. The guide piles served the same function as at the Brooklyn Bridge, keeping the massive timber and iron boxes descending vertically as workers excavated the soil beneath them. An 1877 engineering textbook by H.A. Wheeler, reviewed by the Geo Institute, noted dryly that the health of the workmen was greatly affected by the high degree of compression of the air in which they had to work, and several lost their lives in consequence. The official language concealed a grim reality. Men went into those pressurized chambers healthy and came out with joint pain, paralysis, or worse. In Chicago, the foundation problem was different, but equally instructive. The 1889 auditorium building, designed by Dankmar Adler and Louis Sullivan with engineer Paul Mueller, sat on soft blue clay that extended more than 100 feet deep. Standard pile driving did not work in that soil. The piles simply could not find firm bearing in the soft, wet clay. So Adler abandoned piles entirely and designed a floating raft foundation made of crisscrossed railroad ties, topped by a double layer of steel rails embedded in concrete and coated with pitch. Over 30,000 cubic yards of earth were removed before the raft was laid. The building still stands today on Roosevelt University's campus. Its enormous weight distributed across the raft, like a ship floating on a sea of clay. When Adler's consultant, General William Suey Smith, later specified traditional wooden piles for the adjacent Garrick Theater, the pile driving shook the ground so violently that it caused severe structural damage to neighboring buildings. Work was halted, and Smith switched to hand-dug caissons for the remaining foundations. The lesson was clear. Pile driving in soft ground was not just difficult. In the wrong soil, it could destroy the buildings next door. Every one of these mega projects, the Brooklyn Bridge, the Eads Bridge, The Chicago Auditorium revealed the same truth. The foundation was the most dangerous and unpredictable part of the entire job. The towers, the cables, the steel arches, those were engineering problems with calculable solutions. But the ground beneath them was a gamble. You drove your piles or sank your caissons and hoped the soil cooperated. When it did not, men died. And even when it did cooperate, the methods required to reach solid ground were punishing beyond anything most workers had ever experienced. The human cost of pile driving in the pre-hydraulic era is difficult to quantify because the men who died doing this work were rarely counted. They were immigrants, itinerant laborers, boatmen hired for a season. Their names appeared in parish records and coroner's reports, if they appeared at all. But we have one case study that reveals the reality with painful clarity. The Forth Bridge in Scotland, built between 1883 and 1890, is one of the most iconic steel structures ever built. Its 3 massive cantilever towers span the Firth of Forth, and the project required thousands of foundation piles driven into the seabed before any steel went up. The official death toll published by engineer Wilhelm Westhoven in his report of 1890 was 57 workers killed during construction. But that number was wrong. The Briggers research team, led by Frank Hay, Jenny Meldrum, Len Saunders, and Jim Walker, and written up by historian Elspeth Wills, spent years going through parish records, hospital admission logs, and company pay accounts. They raised the confirmed death toll to 73. The breakdown tells you everything about the dangers of heavy construction in the Victorian era. 38 men died from falls. 9 were crushed by equipment or materials. 9 drowned in the Firth. 8 were struck by falling objects. 3 were killed in a workers' dormitory fire near the village of Aberdour in October of 1888. 1 died of caisson disease from working in the compressed air chambers of the bridge's underwater foundations. 5 deaths remain unexplained in the records. Among those 73 was a teenage riveter named Thomas Shannon, who fell from the steelwork and landed at the feet of his own father, Patrick Shannon, who was working the same span that day. Another was an Italian diver named Thomas Liberale, suspected to have died from the effects of working under compressed air in the underwater foundation chambers. The Forth Bridge was a well-documented, high-profile, government-supervised project. The countless smaller bridge, wharf, and harbor jobs across the world had no such documentation. We spent weeks tracking down records from this period, and the pattern is always the same. The structures survive. The names of the men who died building their foundations do not. Consider what working on a pile-driving crew in the 1880s actually meant. You stood within arm's reach of a heavy iron ram that rose and fell dozens of times per minute. The noise was constant and deafening. There was no hearing protection. After a few seasons on a pile-driving job, permanent hearing loss was virtually guaranteed. There were no hard hats to protect against fragments of shattered pile heads that flew off with each blow. There were no safety lines on the leads, the tall wooden or iron frames that guided the pile and the hammer. If you slipped on the wet, muddy platform, you fell into the water or onto the ground below, and the work did not stop for weather. Pile driving was seasonal work, concentrated in the months when water levels were low enough to expose the riverbed or shoreline. Crews worked through rain, through cold, through fog, because every day of delay cost money. The men who did this work were tough because the work demanded it. They did not call themselves construction workers. They called themselves pile bucks, and they were proud of it. If you are finding this valuable, hit like and subscribe. We bring you stories from construction history that deserve to be remembered. The term comes from the butt end of the pile, the large, blunt, impacted end that the hammer struck and that the worker stood closest to during operation. Folklorist Archie Green traced the earliest print appearance of the term to an article in the Industrial Workers of the World newspaper, The Industrial Worker, dated October 10, 1912, about Pile Drivers Local 77 in San Francisco. The modern trade publication Pile Buck Magazine, still in circulation today, was founded in 1984 and takes its name directly from that working-class tradition. One of the few recorded artifacts of the human experience of pile driving comes from the Library of Congress. In 1934, folklorist John A. Lomax traveled to Montgomery, Alabama, and recorded a man named Willie Williams singing a pile-driving song. The recording, preserved as Library of Congress archival item AFC 9999005.784, captures the rhythmic chant that pile-driving gangs use to coordinate their hauling. When 30 men are pulling on ropes tied to the same ram, they need to pull together, or the hammer does not rise evenly. The song was not entertainment. It was the timing mechanism that kept the crew synchronized so the hammer fell on beat. Similar chants from Caribbean and Thai pile-driving crews survive on film today, living echoes of a tradition that stretches back centuries. The transition away from the methods described in this video happened in stages, each one building on the last. The first major shift was the material of the pile itself. For thousands of years, piles were made of wood: oak, pine, elm, whatever timber was available locally. Wooden piles rotted below the waterline, were eaten by marine borers in saltwater environments, and had a limited bearing capacity determined by the species and diameter of the tree. The search for a better material led to two parallel inventions on opposite sides of the Atlantic. In 1897, French engineer François Hennebique introduced reinforced concrete piles in Europe, replacing the traditional timber stakes that had been standard since the Romans. That same year, on the other side of the Atlantic, Alfred A. Raymond founded the Raymond Concrete Pile Company in Omaha, Nebraska. Raymond's core innovation was the tapered shell and mandrel system, protected by United States patent numbers 589,026 filed. August 31st, 1897, and 700,700. 7. Filed May 20th, 1902. The concept was to drive a thin, tapered steel shell into the ground using a removable solid core that transmitted the hammer blows. Once the shell reached its target depth, the core was extracted and the hollow shell was filled with wet concrete, forming a permanent tapered concrete pile. The first Raymond concrete piles were installed in a Chicago building foundation in 1901, each designed to carry 30 tons or more. Raymond would later supply piles for the Golden Gate Bridge and the Pentagon. The next leap came from Germany. Delmag, founded in the city of Esslingen in 1922, patented the first combustion-powered impact hammer in 1927. Instead of an external steam supply, the Delmag hammer used the detonation of diesel fuel injected into a cylinder to launch the ram upward after each impact blow. Chief designer Haga refined the principle of impact atomization in the immediate post-war years, and the first production model with a 500-kilogram piston, the D5, was built in 1940. In the United States, Syntron licensed the Delmag concept and added engine-style atomized fuel injection, plus a dashpot bounce chamber. The technology then passed through Linkbelt and eventually to ICE, which continues to manufacture diesel pile hammers today. But the era we have been describing did not truly end until 1969, when McKiernan Terry, known in the industry as MKT, introduced the V10. It was the first American-manufactured hydraulic vibratory pile driver. Vulcan and Foster had already brought Japanese and French licensed vibratory units to market in the early 1960s, but the MKT V10 marked the point where American manufacturers fully committed to hydraulic technology for pile driving. From that moment forward, the pre-hydraulic era was over. That means the age of pile driving without hydraulics lasted from roughly 500 BC to 1969 AD. 25 centuries of hitting wood with something heavy. From Caesar's legions on the banks of the Rhine, to Nasmyth's 4-ton steam hammer at Devonport, to Vulcan's 60 blows per minute rigs hammering the waterfronts of Chicago and New York. The men changed. The empires changed. The hammers got bigger and faster and louder. But the fundamental principle, lift something heavy and drop it on a stick, remained the same from the Roman fistuca to the last steam hammer retired from an American job site. The next time you drive across a bridge or walk into a building that was built before 1970, the foundation under your feet was almost certainly put there by one of the methods we described in this video. Wooden piles hammered into mud by men who could not hear each other speak over the noise of the ram. Steel piles driven by steam hammers that shook the ground for blocks in every direction. Concrete shells pounded into clay by diesel detonations that echoed off the buildings around them. Every one of those foundations was placed by a crew that accepted risks we would never tolerate today. And every one of those crews did the work because somebody had to. It all started with a sharpened log and a heavy rock, and it took 25 centuries to find a better way. If you found this valuable, hit like and subscribe. We cover the machines, the disasters, and the people behind the greatest construction projects in history. We will see you in the next one.